Hey, welcome back. Dr. Clark here as always, and in this video we're going to take a look at how to do inference for multiple proportions using a theory-based approach. Let's take a look. So when we're comparing multiple proportions with a theory-based approach, we're going to be using some similar ideas to what we did with the simulation-based approach, but there'll be some subtle differences. So if you remember from Section 8.1, the simulation-based method used the MAD statistic as a way to take all of the differences in proportions and combine them up into one average that sort of quantifies how different the different proportions are from each other, and then to see if that's significant evidence that that the true population proportions must not all be the same. If you do a simulation approach, it's good because it kind of builds intuition for what inference is really doing with multiple proportions, but it does require a computer to do a simulation. Now, when we do a theory-based approach, we're not going to be using the MAD statistic. We're going to use the chi-square statistic. And that's essentially for reasons beyond the scope of this class. But there are technical reasons why professional statisticians prefer the chi-square statistic. But for our purposes, it's a very similar thing. It's just a slightly different formula with how it takes the different proportions and compares them. But because it's a theory-based method, it's standard and reproducible. Everybody will get the same p-value because it's all following one theory-based distribution. But you do have to check the validity conditions that they're met. All right, so what is this chi-square distribution? Well, it's going to look very similar to this MAD distribution that we've seen before. Now, previous null distributions, when we did theory-based approach, we had the normal distribution and the t-distribution. They were both bell-shaped, usually centered at 0. That's not going to happen in this case. The chi-squared distribution, as was the MAD statistic distribution, has this sort of boot shape to it. And it's skewed to the right, so it's not going to be a bell-shaped curve. Now, what is the chi-squared distribution? And this is the Greek letter chi, so it kind of looks like x squared, but it's the Greek letter chi, so it's called the chi-squared. Instead of averaging the absolute values, we sort of average the squares of the differences. So if you take the differences and square them, that will also make positive numbers, and then you can sort of average up those squares. And it turns out that there are sort of technical reasons why that's a little bit better than doing absolute values in sort of mathematical reasons. So there's sort of two ways to do it. This is the way that probably makes the most sense. If you take the p hats, that's in your sample, and subtract them from, so this p hat would be, if you took all of the data and averaged them all together to get what is the p hat for the entire, for all the data. And then this would be each column of the data. And so when you're subtracting them, you're sort of seeing the difference between each individual choice for the explanatory variable and what you would expect to have happen. And then you're squaring them, and this sigma sign means adding them all up. And so this is called the chi-squared statistic. This is a different way to do it. This says observed minus expected squared divided by expected, and then sort of all added up. You don't have to know in this class how to do these formulas. The applet is going to do it for you, but it is good to understand that, okay, what we're doing is we're sort of saying how different are these proportions from each other. And that's really what you can kind of see here. We're taking a difference in the proportions. All right, and it's squaring them. That's where the squared comes from. And so why would we do this? Well, it's a nicer theory-based distribution. We know the shape of this curve, and so this would be what professional statisticians would actually use. Okay, but it's very similar to the MAD statistic in that the larger the chi-squared statistic is, the more evidence we have against the null. The shape kind of looks like this, so when your chi-squared statistic is really big, that tells you that the null distribution is probably not true. 0 would mean that all of the p-hats were the same, and so when you subtracted them from each other, you got 0 every time, right? And then you wouldn't have any evidence that the true proportions were different because all the sample proportions were the same. The more the sample proportions are different from each other, the more evidence you have that the true proportions must not be. And we're going to use the multiple proportions applet to do the chi-square statistic or the MAD statistic. It will do both, and it will do a simulation test and the theory-based test. It actually does both of them for you. And the last thing in terms of the main ideas here is there are validity conditions when you use a theory-based test. And it's really just the same as the validity conditions we had before for categorical data. You just need 10 outcomes in each box. But what's going on is you have explanatory variable 1, explanatory variable 2, explanatory 3, and maybe even more. You know, this could be freshman, sophomore, junior, senior. It could be, you know, night light, room light, or no light, right? We've seen that example before. However many explanatory variables, you need at least 10 successes and 10 failures in each box of data in your two-way table, okay? And then that would mean that you have enough sample size for the chi-squared distribution to be reasonable, and then that's when you can use a theory-based test. Okay, so those are the main ideas for what the theory-based test is going to be based on, and we'll see in the next video how to actually do an example problem and how the applet works and how we will you know, generate the distribution like this, and then we'll be able to get our p-value and that kind of thing. All right, so we'll see you in the next video.